Thank you very much. I'm very excited to tell you about my work on metastability in open quantum systems. We've already heard about metastability today in the context of preparing in experiment long-lived states, which are different from the stable phase of a quantum system. But metastability is also something which is present in equilibrium classical matter. In fact, whenever you are close to first order phase transition, so you say you're in the proximity of one, what happens is that the phases which would be stable at the transition point become metastable. And this proximity to a transition can be either due to tuning parameters of your system, or maybe just to the finite size of what you consider. But this is not the only scenario when you can observe metastability. For example, in glassy soft matter, where you have dynamical constraints, what can happen is that the relaxation towards the equilibrium state is so inhibited that you never really observe this equilibrium stable phase at experimental timescales. And all this phenomenon in classical thermal equilibrium systems can be understood by looking at the free energy landscape. You can have multiple free energy minimum, and you can also understand the long-time dynamics this way. But what I would like to talk to you today about is how to do that for quantum and non-equilibrium systems. In particular, I would like to focus on systems where you can observe distinct metastable phases, which I will refer to as classical metastability. I will present quite an abstract approach to the problem because we're no longer at equilibrium, but then I will arrive at an example of a glassy open quantum systems where hopefully all these results will be visible and clear. And so let me start with what is the setup I'm thinking about. So I'm thinking about a quantum system which is interacting with environment. This interaction is weak, and also the timescales of the environment are much faster than those of the system. So what happens there is that if you wait for a long enough time, you expect your system to relax towards asymptotic state, so-called stationary state, which doesn't change with time anymore. And this system, depending on the type of interaction, but usually will be out of equilibrium. What I'm interested in is how you reach that stationary state. And in the setup I've just described, you can write dynamical equations for the density matrix of your system. And the equation will be linear in the density matrix. And this super operator is called Lindbladian, which you've just heard about in different contexts. And what I will use is the fact that, of course, the whole physics is encoded in this equation, but I'm not showing it to you because what I will use is the fact that it preserves the positivity and hermiticity of the density matrix. So what is this phenomenon of metastability I will tell you about? Well, if I'm close to the stationary state, I'm in the final regime, I know that the changes in the observable averages, such as magnetization of a spin system, are not big. But what can happen is that there's a distinct regime when the changes of my observables are very, very small. But this is not a stationary state anymore because what I observe is actually very distinct from the observable value for the stationary state, shown here in red. I don't have to do averages. I can also consider observable correlations instead. So what I have here is this separation of timescales when I have initial relaxation towards the metastable regime, and then I have long-time dynamics towards the stationary states, and the timescales which are characteristic for those are very, very different. So all this is very plausible, and I'm sure it kind of captures your intuition about the phenomenon itself. But what I would like to do, I want to have a formal quantitative definition. So how to do that? Well, I will go with this experimental intuition that I want to measure some observables and see how they change, how the averages change in time. And what is important is to consider logarithmic timescale, because this is actually due to Markovianity of the dynamics. So what it means that I will look at the time and then it's double, and I will ask myself, okay, how much is the change of my observable? And then I have to normalize it by the range of possible values I can observe. And in that case, it turns out that if I assume that I'm shorter than the longest time scale in my dynamics, so-called relaxation time scale, then I can show that there exist system states which are very different from the stationary state itself. And this is shown by the distance in the trace norm, which is bigger than 1 in the leading order. And the maximum value of this is 2, so we're not quite there, but we're very different from 0. So what I would like to understand is now how these states really look like, because I know they are different from the stationary state, but what they really are. And to do that, I will use another property of the master equation, the fact that it acts linearly on the density matrix. So if I think of the density matrix as a vector, what I can do, I can decompose the matrix, the Lindblad operator, as into its eigenbases. And here I have these modes, right? Eigenmodes are k, and I have eigenvalues lambda k of the master equation, and then I have coefficients of this decomposition. And I can ask myself, what are the properties, of course, and what I will see is that all the eigenvalues are negative in the real part, so that when I wait for a long time, I get to the stationary state. But what I expect at metastable regime is that they will not be changing much. And in fact, if I plot now this evolution, this exponent of the eigenvalues for the times in the metastable regime, I will see that they follow two possible cases. So either I am close to 0, so certain modes have decayed, and this can be quantified by these changes in observable averages, or I'm close to 1, which is what I expect for the stationary state itself. And this doesn't just happen for any master operator. What this can be translated into is a separation in the eigenvalues of the master operator itself, which you see here. And this separation can also be bounded from below. So I have a situation which almost looks as if I was at a phase transition. Namely, at a phase transition, I would expect to have multiple stationary states and multiple eigenvalues of master equation being 0. But I don't have it, but I can try to do something as if I was there. So what would be? Well, I have the approximation of the eigenvalues, so I can use it and pull all the blue eigenvalues which are slow towards 1 and the rest towards 0. What it means then is that my state is described just by the number of coefficients which is equal to the low-lying modes. So what I started with is probably a highly dimensional Hilbert space. So if I have a spin chain, for example, it will be 2 to the n, where n is the number of spins. And then I reduce it to just this number of slow eigenmodes. So this is very nice in principle if I can do that, because I can no longer care about the degrees of freedom which were encoded in the fast modes, and I can describe my states now by just coefficients. So I can take initial random states and plot it if I'm not too high in dimension, and see what is the shape that the set of metastable states takes. But of course, this doesn't come for free. What I just done is I took a lot of modes, squaring the dimension of my Hilbert space, and I approximated them all at the same time. So in principle, you could expect that this can fail very easily. But it turns out that generically it is true. So again, again, the errors of these approximations, which is just the tape measure here, I can measure in the trace norm, are bounded by the changes of my observables. And there's a little asterisk there, which means that this is not always the case. And when it is not the case, what must happen is that either the approximation of the fast modes fails. In the leading order, it fails that the errors at least of the order 1, or the approximation of the slow modes fails in the similar fashion. So we have very extreme cases, and I will focus on this case when it works nicely, and I have this efficient degree description of my system. So what I can do then, I can say, well, I want to go beyond the metastable regime, and to do so, I will include the decay of the slow modes. And what it does, well, it shrinks this metastable manifold described by the coefficients towards the stationary state, which is here shown in red. Moreover, what I can do, well, I can look at different observables and use the same approximation, and what I will see is that both in the metastable regime and beyond, I have a really good agreement. The same holds for observable correlations, and in fact, the errors are even smaller than those of the procedure within the metastable regime. This is all very nice. In fact, if you have any dynamical symmetries, what will happen is that the coefficients, the set of coefficients will be invariant under those, and also at any later times, this invariance will be preserved. So any dynamical symmetries are inherited during the metastable regime and afterwards. But you can ask yourself, okay, what are really the things I'm seeing? What is the physical interpretation of this a very simple picture? And in fact, this is a non-trivial question because the eigenmodes of the master equations are not states. If you look at the trace, it is actually 0. So what it means that you cannot think of them, all right, I have just another density matrix there. I have to think of it as an excitation over the stationary state. So I would like to tell you how to interpret those remaining degrees of freedom, these coefficients CK, in a very particular case, which I call classical metastability. Classical metastability I will define in an intuitive way where degrees of freedom, I'm kind of putting them auxiliary, are probability distributions. So I can choose a fixed number of states, and everything can be approximated as their mixture. So if I start with such a picture, I can use it to go from this unphysical basis of eigenmodes towards something which is much more physical, towards the projection on the slow modes of these phases I kind of assume the metastability corresponds to. If I do that, then it turns out that the corresponding coefficients, the barycentric coordinates, have to be very, very close to the probability distributions. So I have an efficient way of verifying numerically that the classical metastability, in fact, holds. But where I started was the fact that I had some candidate states for which this classical metastability really correspond to probability distributions. And I have to be able to generate those. And in fact, we proposed an algorithm to do so. And we used it to look at an open quantum East model, which is a generalization of classical East model known to display glassy dynamics. So let me tell you now a little bit about this model and what are the results for it. So what I have is a spin chain. This spin chain is in the contact of
Kasia, just a heads up, you have about 6 more minutes.
Great. So I have spins which are in the contact with a heat bath at a finite temperature. So I have kappa for emission of photons and gamma for absorption of photons. And then I also, to make it a quantum, I have a transverse field. So far I haven't added any interactions. So each of the spins evolves independently, and I see it in emission trajectories. So not only on average dynamics, but also if I think what are these photons really emitted from the system. And even if I have low parameters, I have weak field and low temperature, there is no transition in the system because everything is a product state. So now I will try to add an interactions, and the way I will do that, I will add a constraint so that the dynamics, including both dissipation and the driving, can only proceed if the neighboring spin is in a particular state. And if that state commutes with the stationary state of a single spin, what you will see is that the stationary state actually won't change. So although I introduce interactions, there is nothing left from that when I look at the stationary state. But if I look at the trajectory again, at the emission pattern, in this limit of weak field and low temperature, what I will see is that there are really rare excitations because it's so difficult to fulfill the constraint, which is towards the excited state. And this is known as dynamical heterogeneity. And although this is stochastic dynamic, I can look at the master equation and see this separation of timescales when it comes to its eigenvalues. And I have two gaps in the spectrum, and they correspond actually to the hierarchy of metastabilities. So what I can do, I can use this numerical procedure and check that actually this metastability is classical, and in both cases. So let me tell you what are those metastable phases I'm seeing. When you look at the trajectory, there is no surprise. What I see is a metastable phases which has no excitation. Here I'm showing the magnetization up or down state. Then I have states with a single excitation or with double excitations. And what I can observe is that these states are orthogonal. They are very distinct, live in a different parts of the Hilbert space. And I also have translations of them being metastable. And what it means is that although I break the symmetry present in the system with periodic boundary conditions, it is restored overall when I look at the whole set of metastable phases. I can also look at this physical basis and ask myself how the master operator looks like in it to understand the long-time dynamics. And what I will see is that this master operator looks almost like a classical generator. So I have something which is negative on the diagonal, and then almost positive, approximately positive off diagonal terms. And I have this matrix acting on a single excitation state, and then, sorry, on a zero excitation, single excitation, and two excitation states. And what I see is the structure similar to the stochastic trajectory. So the shortest lived states are with double excitations. Then I have states with single excitation, living a little bit longer, but the longest by far is this state when there are no excitations, and this inactive phase, which we observe in the trajectory as well. All these features are actually not due to the peculiarity in some sense of the model with these dynamical constraints, but are general features of classical metastability. So if I have these metastable phases chosen so that my approximation of degrees of freedom is truly classical, I can show they can be orthogonal, which manifests itself as a distance in the trace norm equal to. I can show that any dynamical symmetry, in fact, has to be a permutation of metastable phases. And it means that there can be no non-trivial continuous symmetries. And if I look at the dynamics itself, it can be approximated by classical stochastic dynamics. And this stochastic dynamics, which I will see as a generator, will in fact govern the emission trajectories. So all these features come whenever you look at this geometric criterion of approximating your metastable manifold by probability distributions. And with that, I'm arriving at my conclusions. So today, I tried to tell you about metastability in non-equilibrium quantum systems. I used a phenomenological motivated criterion to quantify how metastable the system really is. Then I linked it to the properties of the spectrum and showed that typically I will be able to describe system in terms of the decomposition into the slow modes. And I also talked about the case, where these remaining degrees of freedoms are classical. But of course, it's not the end of the story. The first step would be to ask what are the other possibilities and other characteristics of remaining degrees of freedom. And this can correspond to quantum metastability when you have metastable coherences. The other direction would be to ask, what if this spectral metastability approximation doesn't hold? So either these fast modes cannot be neglected, or the decay of slow modes cannot be neglected. And the last case is to ask yourself, is that the most general definition of metastability you can have? And the answer to that is also no. And this is because they can be persistent oscillations in open quantum systems, which we'll hear about on Wednesday from Verislav Buka. And in that case, you don't have approximate stationarity, but you can have approximate stability of your system. And I would like to generalize this approach I presented here to those cases as well. And with that, thank you very much for your attention.